BC Calculus, lesson 10.3, Taylor's Theorem. Warning, one of the most challenging things we'll do all year. Concept's not that hard. You know, we're going to say, great, we can approximate polynomials. How good is our approximation? And this is the big question. The only good news I have is you do not have to get too worried about all of this. It's going to work itself out. If you understand what a Taylor series and a Maclaurin series is and a general idea of how to find the error, you're in good shape. The big question comes as things like this. Find a Taylor polynomial. I'm going to program it in. I don't know how to put sine into this machine, but I do know how to put polynomials in, which can serve as an adequate substitute for sine of x on this interval. And that's the question to answer is, what do we mean by adequate? So sine of x, according to last unit, is x minus x over 3 factorial plus x over 5 factorial, dot, 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 minus technically dot, dot, dot. Let's do that many terms, see what happens. According to my calculator, sine of, and we go out at the end of the endpoints, sine of pi, and even if it wasn't a closed interval, we would use those endpoints because they're going to set the worst case. Sine of pi, of course, is 0 last I checked. So pi minus pi to the third over 5 plus pi to the, I don't know what that was all about, over 6 plus pi to the fifth over 120, just using a fifth order Taylor polynomial. I'm going to put this into my calculator even though I have the number somewhere else. Point out a couple things as we go along. We get 0.524, which clearly I did something wrong. Not sure what I did wrong. I guess we'll just have to go out further. Minus pi to the 7th over 7 factorial plus pi to the 9th over 9 factorial minus pi to the 11th over 11 factorial. So I'm going to put those into my calculator too. Minus this does take some time. Especially when you screw up. And last one, pi to the 11th divided by 11 factorial. And I get a really, really small number. I get negative 4.452 times 10 to the negative 4th. Pretty close to 0. My error is, and we always take absolute value, would be 4.452 times 10 to the negative 4th. If I had gone to one more term, I would have gotten 2.114 times 10 to the negative 5th. Notice it's positive now. It drops below, above, kind of like this as it searches for the answer, in this case 0. First term's positive, so then it kind of gets closer and closer and closer. So how good is that? I mean, is that adequate? It would seem adequate to me, you know, accurate to 3 decimal places or 4, or whatever you want to call it. Well, we can get something we call truncation error because we stop at a certain term. So for this one, the truncation error is going to start at x to the 8th, because we're going square root 4th, 6th. So if we know that the actual, and this we should know, it's 1 plus x squared plus x to the 3rd. Oh, wait a minute, x is x squared, so that's squared. So on and so on. Actually, we'll write it out. 1 plus x squared plus x to the 4th plus x to the 6th. Then over here, x to the 8th plus x to the 10th plus x to the 12th. So this is what they said, well, we're just going to use this. How big is our error? Well, we say, well, the error is going to be whatever's left over, all this other stuff, and it'll be the absolute value. Well, we can write this, since it's geometric, as first term over 1 minus x squared. We should definitely put absolute value around it, because it's an error now. So that's going to be our truncation error. And we can actually calculate what it'll be depending on what the x is. X has to be in the interval, otherwise we have a problem. And since x to the 8th is always positive and x squared is always positive, we can just write it like that. We call that our error, and we'll get into that a lot going forward. I would like to overemphasize that there's a lot of confusing stuff that I'm really struggling with, feeling confident about going forward. But if you get these general ideas, then you'll be fine. So like we just said, that works very well for a geometric. What if we have a non-geometric? So now we get super high theory. If we have a derivatives, if the function f has derivatives on all orders in an open interval I, and that I interval contains a, could be 0, could be something else. For each positive integer n, we have the series, which we know about. And we usually end it somewhere here, but now we're going to say plus a remainder. And that's like our truncation error. We're just saying, I mean, this is a brilliant idea. Hey, wait a minute, we'll just stop at some n order. And everything else is a remainder, which we will eventually call an error. So the remainder should go on forever and ever. But what we do is say, we know that that term will be the biggest. All the other terms are going to be smaller to the point of insignificance, and they're going to go, generally, well, we don't know if it's an alternating series, but there's going to be the bound. That's going to be the biggest error we get if we round it correctly too, of course, because it won't affect the first few decimal places. So this is Taylor's formula. The remainder is also called the Lagrange form of the remainder. And it sets bounds, not the errors. It's the worst case scenario. The bound will actually be a little bit less, because we're not always working at the endpoints. So if the Taylor series converges, we say that the remainder goes to 0 as n gets to infinity, as long as we're inside of I and all the x work in there. So this is the actual one, if x equals a converges to f on I. If you lost you there, then don't worry about it, I lost myself. So prove that this converges to sine of x for all real x. Now this is pure theory, but we look at the remainder theorem. Remainder of some order n, we don't know, but we're going to say what happens when r of n, what happens r of n as x approaches, n approaches infinity. So the formula is r sub n of x equals the next derivative, one order higher, of some random c. We don't know. I don't know anything about this c. And we are going to go with x minus 0. Now I have to figure out why. Yeah, I know why. Because we're doing 0 to infinity. And there's our formula. I'm bothered by the 0. I'm bothered by it a great deal. But it's some zero between, some C value here between x and 0. And you'll see how we're going to prove that it works going one way, therefore it has to work going the other way. We'll get to that shortly. So, when you look at this and you go, great, that doesn't really do anything for me. Well, if we're doing sine, which is what that represents, what's the derivative of sine? Well, it's cosine, sine, cosine, some positives, some negatives, that sort of thing. Dot, 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 dot. That never gets anywhere but up to 1 and down to -1. It bounces around in there. Now we're going to take the absolute value because it's a remainder and we just want to know what it is as a quantity, not as a sign for it. And we know that the top's going to end up being 1. This side is going to be x to the n plus 1. And this is going to be n plus 1 factorial. And here is the important part. Factorial will grow faster. No matter what x you pick, I pick a billion. Eventually that factorial, as n goes to infinity, will become a billion plus 1. Factorials grow fastest than anything. We use this expression, it will sweep the remainder to 0. So we get remainder equals 0. That completes the proof. You might say, well, wait a minute, why 0? Why not a? Why not? It doesn't matter. It's some x minus 0. It could be x minus a billion, and it's already a billion. It could be a negative billion minus a billion. It doesn't matter because that grows so fast. Goofy stuff. We got to look at this again. This is what I just said about the n plus 1 factorial. It's bigger no matter what. And it will always outstrip exponential growth, which is the fastest one we know, or did know. This gets bigger exponentially. If x minus a greater than 1, smaller exponentially if x minus a is less than 1. So that matters depending on what you're dealing with. As we just said, we just showed you it's gonna get bigger on the bottom no matter what. So all we really care about is what's going on over here. Is the derivative getting bigger and bigger and bigger and bigger? If it's getting bigger and bigger and bigger, is it getting bigger and bigger and bigger with the other top to outstrip what's going on the bottom? Here the theory eludes me, and I'm going to skip my next example. I'm going to cut to the chase. Here it all is. They give you this random stuff. M standing for maximum, which took me a long time to figure out. R meaning a derivative substitute, like the ratio. And that one was not even remotely clear. We can say converges, blah, 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 blah. Here's an example. It's horrendous. I'm not going to try and sugarcoat it at all. But the long story short is that exponential bounds, the maximum is e to the 7x. And if I take the derivative, I get 7 to the n plus 1. So that's my r value. Long story short, the bottom's going to get bigger faster. And we can say that, and again, I'm just going to blow through it. e to the 7x converges for all x. This is back to a little piece of memorization. Don't sweat that one, just know for sine, cosine, and e to the x, all x, because of this little theorem. More importantly, can you do it here? We're going to talk about a maximum error. We're going to call it M. And we're going to say, we did it with 2, so the third derivative of this thing, f prime is 1 over 1 plus x, f double prime is negative 1 over 1 plus x squared, and f triple prime is 2 over 1 plus x to the third. So the maximum is going to be 2 over 1 plus, and it may be less than or equal, it might be just less than, so don't worry about this greater than or equal thing. 1 plus, and we'll do the negative 1, just for the fun of it. It doesn't really matter. Well, since the natural log is naturally decreasing, it's going to get bigger this way, so we can check it with both and see which one gets us there. Parentheses to the third, that equals 2,000 over 729. So that one's tricky. You got to check that out. You got to check out both endpoints. We're looking for the worst case scenario. So the remainder of x is that 2,000 over 729. That bounds it. That's the worst case. Times plus or minus 0.1 to the third over 3 factorial. This is the next term. All right, and that is going to be less than 4.6 times 10 to the negative fourth. Now, I don't get it. I say, well, let me just go and check my next term, x to the third over 3, which if I put in for negative 0.1, yeah, all right, so that's the bound. By the way, this is rounded up just to be safe. You can actually calculate what it is, and if you put in negative 0.1, it's a little bit worse off. Goodness gracious. Yeah, I have to double check my math here, but I will do that later. R of 2 of negative 0.1 equals 3.605 negative, but we're going with an absolute value of 3.605 times 10 to the negative fourth, which is the actual error, which is less than the bounded error. So that's a bit of what's going on. Don't get hung up on this. Play with it. It'll be fun. Now we get to have a little bit of fun. Not much, just a little bit. Find the Maclaurin series for e to the ix, which is particularly complicated, or should be. We just plug in ix, so e to the ix equals 1 plus ix plus ix squared over 2 factorial plus ix to the third over 3 factorial, dot, 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 dot. If you know anything about imaginary numbers, you would get 1 plus ix minus x squared over 2 factorial plus, minus x to the minus ix to the third over 3 factorial plus x to the fourth over 4 factorial, dot, dot, dot. Complicated stuff. Now, this proves that cosine x plus I sine of x, because cosine of x is something I gotta go find. Cosine of x, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, dot, 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 and I sine of x equals I of x minus I x to the third over 3 factorial plus I x to the fifth over 5 factorial, dot, dot, dot. And you can see if you add these together, you get this. 1 plus ix minus x squared over 2 minus I. And so you've just proved that e to the ix equals cosine of x plus I sine of x. I will leave it up to you to try that one, which is kind of a whoa moment. E to the ix plus I equals 0. That's a little scary. That is it. For once I mean it more than I usually do. Happy mathing.